All right, I want to finish this example now, just as a refresher. Here is what we're analyzing. We're analyzing this structure that has friction piles and a basement. And so we have separated out the pressure. We've drawn the pressure bulb for the piles, which is at the 2/3 L down, and we've drawn the pressure bulb for the basement, which is from the basement. And then we have determined, well, we've got our point of interest is at 79 feet, and we've already found the sigma prime I, that is the effective stress at 79 feet before the structure is built, and we have the OCR as given. We got the sigma prime P. Okay, so now we want to analyze this, and we're going to break up. Now we have to separate out the piles using the pressure bulb for the piles and using the pressure bulb for the basement. And so we've got the center, edge, and corner for the piles. And we have the center, edge, and corner for the basement. So let's do the piles one first. And the P is what? This is the weight of the structure. The weight of the structure, 1.5 million pounds. The area, the width is 36, so 36 squared, that gives us the area. So in other words, we have those piles underneath the whole structure. The Q is equal to P over A. That gives me the Q. The Z is the depth to the point of interest, the depth from, not the depth to the point of interest, the distance from the foundation to the point of interest. So for the piles, it's 36 feet. That's for the center and the edge, and then we do our little trick for the corner where we divide it by 2. The width B is 36 feet, because that's the building width. We simply take Z over B. And then I'm not going to go through this again, but we do our pressure bulb factor. So this is below the center, this is below the edge, and this is below the center. We get the contour, we divide it by 4 for our little trick for the corner. And then what do? We take the pressure bulb factor, we multiply it times Q, and we get our delta sigma V. Okay, so now we're going to do the basement. Well, now we're going to use the basement. So what do? I need to figure out, okay, what is the weight of the soil that we've removed? Well, we have the volume of the soil times the unit weight. So there's my unit weight, 110, and the volume of the soil is what? 36 squared times the basement depth 9. So the volume is 36 squared times 9. The unit weight is 110, so volume times density is going to give me weight. That is how I get my P for this. The area, again, is 36 squared. And then I take P over A. That gives me Q. Now my Z, again, now here I have to do what? There's my point of interest way down here. And so that's a Z of 70, because we determined that 79 feet was the point of interest based on the pile foundation, because that's where most of the changes are taking place. So we stick with that point of interest, 79 feet, and So that gives me a Z of 70 feet because the basement's at 9 feet. So we get our Z of 70, 70, and then we do our little trick, 35 for the corner. The B is 36 again, and then our Z over B. And then notice, so the Z over B is pretty big, 1.94, and over here it's 1. So that means what? That means that I'm going to get a small pressure bulb factor. Small pressure bulb factor. And then a really small pressure bulb factor for the corner. So that tells me that the influence of the basement is going to be much reduced. So I take the pressure bulb factors, again, multiplied by the Q, but now I get that, but I put in the negative sign. Why the negative sign? Because we're removing the weight. Removing the weight, so it's a negative. So now what do? I take, to get my, again, I'm going to do the center, edge, and corner now, and I'm going to combine the piles and the basement effect. How am I going to do that? Well, I'm going to take for the center, 393 for the piles, negative 119 for the basement. So I go 393 minus 119. I'll go 289 minus 89.1. 289 minus 89.1. And then 202 minus the 84.2 for the corner. Oops. 202 minus 84.2 for the corner. So that gives me my delta sigma V. Well, okay, so now I have my sigma prime I, 3694. I've got my delta sigma V given there. I sum them to get my sigma prime F. You can take a look at that. Pause the video and take a look at that. So I now have my sigma prime F. I've got my sigma prime I. I've got my sigma prime P. Everything I need to do my settlement calculation. And so I do one for the center, for the edge, for the corner. In each case, the sigma prime P is put on the inflection point, the 4803, the 4803. And then I put on my sigma prime I, the 3694, so that goes there, there, and there. And then I just have to put on my sigma prime F, and I look at it and I see that sigma prime F is less than sigma prime P, so it's going to go to the left of each one. So I've got my sigma prime F's there, which means that what? That I just use the C epsilon r portion of the curve. C epsilon r is 0.03. So you can all do this calculation by now. So I get my epsilon V. Epsilon V times my H gives me my delta H. You can do that portion. And now what do? I now check my differential settlements, which I'm not going to go over again. So that is how we handle the basement situation. So we have to create the piles and the basement. We analyze them separately. We have two different pressure bulbs. So I have a pressure bulb for the basement. I have a pressure bulb for the piles. That's the main thing that you need to know on how to handle it. And then you can put the numbers in and determine the value of the basement, which may not be much, but it may be. You have to put the numbers on it. So, if your client wants a basement, you can get a basement. It's going to cost something. It may not help the settlement a lot. It depends. Okay, I'll skip that. All right, I want to start with the type 2 foundations. Remember, what is the type 2 foundation? What's the difference between type 2 foundation, type 1 foundation? Type 1 foundation is beneath where the foundation basically supports the entire mat, a mat basically that is underneath the entire structure. Type 2 foundation is where we put the foundation under each column separately. So let's get started with an analysis of the type 2 foundations. Let's take this, so the easiest way to see it is with a little example. And we're going to see that we have to now worry about the columns, how many columns there are. We didn't have to worry about that before. We just didn't care about the columns because we were saying that the load of the structure was basically distributed over the entire mat. And so let's see what the difference is. Let's say our structure weight is 2 million pounds. And so the first thing we're going to want to do is to find the load in each column. Now, the structural engineer can give you this information in a lot of ways, but I want to, for a simple structure that consists of a square and plan, where we have, columns in this distribution here. And so it'll give you an understanding of the impact of the difference in column loads and why they may be different, and how that could cause some differential settlement. So again, when you're in practice, you're going to do something a little bit different, but this gives you the basic concepts. So we're going to use the principle of tributary area, and that means that we're going to take these shaded areas here that represent the tributary areas for each column. What does that mean, tributary area? Tributary means what? Contribute. The root word is contribute. So what area of the structure, what portion of the structure contributes to the load on that column? And so it varies. If I have a corner column, for instance, well, it's only this little region here near the corner. But if I have a center column, well, the center column is going to take more because it's got more area that it's responsible for. It takes half, we're splitting. So in other words, here's an edge column, here's the center column. Well, we're going to say half of this load goes to the edge column and half of it goes to the center, and then the same thing for this one, half, and the same thing for this one, half, and the same thing for this one, half, and the next thing you know, you have this entire area here that the center column is responsible for, whereas the corner column, then it takes half with that edge column and half with that edge column, and it's got less. It's got much less. So just because of the way the geometry of the building is, the corner column is going to take less than the center column, and the edge, same philosophy, the edge is going to take this much, and it's going to be less than the center column. Well, what do we see? So we can just see it. We have the center column is equal to 4. That area is 4 times that one. And then the edge column, well, it's going to be 2 times the corner. So one center is 4 corners. 4 corners is 4 corners, needless to say. And 4 edges is 8 corners, because it's twice as much. So if I look at this, so what do I see? I have one center column, so that's worth 4 corners. I have 1, 2, 3, 4 edge columns, and that's worth 8 corners. And then I have 1, 2, 3, 4 corner columns, and 4 corners is worth 4 corners. So what we're going to find is that we have the equivalent of 16 corner piles. So what do? I take to try to figure out the weight on each column, I'm going to say that the load on the corner is equal to the weight of the structure divided by the 16, because I have the equivalent of 16 corner columns. So if I do that, I'm going to find that I have 125,000 pounds on the corner column. Well, I have twice as much on the edge column, so it's 2 times the corner, which is 250. And then the center is going to be 4 times the corner, which is 500,000. So that tells me the load on each column. Again, I didn't have to do that for a type 1 foundation, but I do have to do it for a type 2 foundation. So why don't you do this one? Same philosophy, but now notice I have 9 center columns, okay? And I have 3, 6, 9, 12 edge columns. And I have 4. We're just going to do a square footprint, so we're not going to get real complicated. We have 4 corners, so we're always going to have 4 corners. But like I say, for a more complicated structure, talk to your structural engineer who can give you the column loads. So we're getting through this, and we're using the philosophy for you to get an understanding of why there's more load on one column than another. So what I want you to do is to find for a 5 million pound structure, I want you to find the center column load. So these are all considered to be center columns, edge column loads, and corner column loads for that. So pause the video and do that calculation. Okay, I assume you pause the video. So what do I have? I've got, as I said, I have 9 center columns, which is the same as 36 corner columns. I have 12 edge columns, so that's the equivalent of 24 corner columns. And then I have 4 corners, which is equivalent of 4 corners. I add all these up, and I get 64 corner columns, which means that my corner column is 5 million divided by 64, which is 78,000. I double that for my edge, and then I double that again for my center. So I now have the loads for each of those columns. So if we have this, so let's take this structure here, and this structure we're going to say has the footprint of this one. Okay, so there is my footprint, and I end up with, we end up with the equivalent of 16 corner columns here. So, here's the philosophy of it. So, first of all, so this is obviously a type 2. It's type 2 because I have my foundation. I don't have basically a mat underneath there. I have individual column footings, and then I have piles under each one. And the width of the pile cap is 10 feet. And so my pressure bulb looks like that. And it goes down to be 20 feet. So the first thing we're going to want to do is to find the center. We got to find our point of interest, which is to find the center of that pressure bulb. And again, how do I do that? Is that, maybe I can write it out here, since it doesn't seem to be here. So what do we have? We've got, so the depth to the bottom of the pressure bulb is going to be what? Well, we have the pile tips. Again, okay, so first of all, before I even do this, notice that these pile tips are in sand. That means they're sand. That means that they're end-bearing piles. So I draw my pressure bulb from the tips. I don't do my little trick of 2/3 and then draw my pressure bulb from there. I don't do that. because these are end-bearing piles. So that's the first thing we recognize. And then what do I see? My pile tips are at 20 feet. And then by coincidence, that's 10 feet. So I go down another 20 feet for my pressure bulb. So I'm at 20 feet. This is going to be at the bottom of the pressure bulb is going to be at 40 feet. So depth to the bottom of the pressure bulb is 40 feet. And the depth to the top of the clay, top of the silt, I'll call it clay, top of clay, because I've been using that symbol, but it's really top of the silt, is at 24 feet. And so how do I get my the depth to the point of interest? See, if I've been using capital D or small d here, maybe I've been using small d. D, D, and then the depth to the point of interest is going to be the sum of those over 2. So that's going to be 64 over 2, which is 32 feet, and our H is going to be the 40 minus 24. H equals 16 feet. So that gives us our point of interest here. And calculation, and it's also written right there, but I didn't go through the calculation. So what we want to do is that we want to find what is going to be the stress at our point of interest. Okay, so what we find is that we have the load from each pile. So this goes back to the previous problem that we did over here. So we're taking these numbers where the center column had 500,000 pounds, the edge column had 250,000 pounds, and the corner column 125. We're using those P's so that we now want to know what is our delta sigma V at the center, delta sigma V at the edge, delta sigma V at the corner. Well, our Q is 500,000 divided by 10 squared, 250,000 divided by 10 squared, 125,000 divided by 10 squared because that is the width of our footing or our pile cap. And then we need to get our pressure bulb factor. Now our pressure bulb factor, notice they're all the same in this particular case. They're going to be the same. The pressure bulb factor is going to be the same. Why? Because because this is small. This width is small. It's only 10 feet. And we are assuming basically that this footing is rigid. If it's rigid, then we're saying that I'm not interested in a differential. If it's rigid, then I don't have any differential settlement. In other words, I don't have a settlement beneath the center of this, a settlement beneath the edge of that, and a settlement beneath the corner, which I can't show, but because it's rigid, and there's no differential settlement. So the entire building base is not rigid, but that little footing we're saying is rigid. So we're going to get the pressure bulb. Now, how do we get there? I mean, we're going to get the pressure bulb factor. How do we get it? Well, we're going to get it, again, we're going to use the point beneath the center of the footing. So we take our Z, so our point of interest depth is 32 feet. The depth to the base of the tips of the piles, which is the base of our foundation, is 20 feet. So 32 minus 20 is 12. So 32 minus that 20 is 12. And that gives us the Z. In other words, this distance is 12 right there. That distance is 12. And the B is 10. That's the width. So I take a ZF over B of 12 over 10, which is 1.2. Then I go into my pressure bulb, and I do 1.2 below the center. So I'm in here, I go down below the center to 1.2, which is there, and it gives me between 0.2 and 0.3 contours, which we're going to take as being about 0.27. So my pressure bulb factor everywhere is, or for each one of these, is 0.27. But notice, because this is 500,000, 250,000, 125,000, what do I find? I get different changes in stress beneath a corner column and an edge column and a center column. So that is really the source of my differential settlement, in the sense is that the stresses are different here. Well, that's where we get different stresses because the column loads are different, not because our pressure bulb factor is different. So type 1 foundation, the pressure bulb factor was different. For the type 2 foundations, it's the column load is different. So that is what we're getting for, that's the source of our, so okay, so we can call them widely spaced or closely spaced. So our type 1 foundation is a mat. Our piles and piers go under the whole mat. And type 2 foundation is that there's more space between the pile groups. And yeah. All right, I'm going to stop there.